So the theorem that's written on the board behind me is the theorem that I'm going to go through next. This is one of the two big theorems really from this first article in Cantor's work. This one I'm going to go through. The other big theorem I'm not going to go through. But just before we make a start on this, there are a few bits and pieces that I just need to introduce, to talk about, so that it's clear what we're trying to achieve here. So the theorem is that if m is a simply ordered aggregate and the cardinal number of m is equal to Lf0, and m has no element lowest in rank, no element highest in rank, m is everywhere dense, then the ordinal type of m is equal to eta. Okay, so part A, we're okay with that, we know what that means. Part B, m has no element lowest in rank and no element highest in rank. That's relating to the order of precedence that's defined on our aggregate m. With it being a simply ordered aggregate, it does have an order of precedence defined on it. So this means that for every element that I choose in m, there is always another element that I can find that precedes that element. So it's got no element lowest in rank. Similarly, for every element that I choose in m, there is always another element that I can find that follows that element. Okay, this C, what it means for m to be everywhere dense. So if between any two elements of my aggregate m, I can always find other elements of the aggregate. So if I know, for example, that m1 precedes m2 in my aggregate m, then I can always find an m3 such that m1 precedes m3 and m3 precedes m2. So it would follow from this that there's there's an infinite number of such elements in between m1 and m2 in the order of precedence, but such an aggregate that has this property is called everywhere dense. Okay, and then finally, what is this eta here? Well, think back to right at the start of this video, we spoke about the aggregate R, which is the aggregate of rational numbers greater than 0 and less than 1. Well, the ordinal type of R and the order defined on it was determined by the natural order. Well, the ordinal type of R is what we call eta. And naturally, the cardinal number of R and the cardinal number of eta is Lf0. And it turns out that R itself is everywhere dense. Is because we know that between any two rational numbers, there is always a third rational number. There's going to be an infinite number of rational numbers. And we know that this is the case for R, and that we've got the first case accounted for as well, the first criteria accounted for. So this theorem is really characterising this ordinal type, that anything that has these characteristics, these features, must have the same ordinal type as this aggregate R. Of particular importance as well in this, in the proof of this theorem, is going to be, my pen's running out. Is the aggregate R0. Now, if you remember, R0 was the aggregate. It had the same elements as R, so it's the aggregate of rational numbers greater than 0 but less than 1. But there was a different order defined on this. It was a much more complicated order. It turns out that the ordinal type of R0 is equal to omega. So I'm not going to prove this, we're going to take it as given, but we are going to need to make use of that. And also, something else that needs to be pointed out is if m and n belong to the class of types, particularly Aleph naught, but actually this would apply to any other class of types as well, but I'm going to stick with Aleph naught because that's the one that we're going to be using. Then if m and n are simply ordered aggregates, but with potentially different ordinal types, then we can always bring m, the aggregate m, kind of reorder the elements or redefine the order so that it has the same ordinal type as n. So that means obviously destroying its original order, rearranging the elements in a particular way so that they correspond, they resemble more those elements of n, and similarly vice versa. The elements of n could be rearranged, break the original order, rearrange the elements and bring it into the form of m. So in the same class of types, any two aggregates can always be brought, by destroying their original ordinal type, they can be brought into the same ordinal type as any other ordinal type or any other aggregate in this class of types here, in this Aleph naught. So we're going to need to make use of this property as well. So that's the preliminary stuff out of the way. So now let's get on with the proof of the theorem. So let's have a look now at the proof of the theorem that I've just stated. So we start off by bringing our aggregate m into the form m naught, such that the ordinal type of m naught is equal to omega. Now if we remember, the cardinal number of m is equal to Aleph naught, and therefore with m naught just being effectively a rearrangement of the elements, we know that m naught, the cardinal number of m naught, is also equal to Aleph naught. They're exactly the same elements, just different order types. So m and m naught are in the same class of types, and therefore, just like I said a few minutes ago, the ordinal type of m can be kind of broken apart, destroyed, and the elements can be rearranged into any into an aggregate of any ordinal type in the class of types corresponding to Aleph naught, in particular this omega here. We've also got R naught, which is our reordered version of the rational numbers, this aggregate of rational numbers, and its ordinal type is also omega. And what we're going to do is we're going to find a correspondence between the elements of R and the elements of M, a one-to-one correspondence, which will turn out to be an imaging as well. And we're going to do this, we're going to need to use R naught and M naught to kind of help us along. So the elements R1, R2, etc. we can think of as elements of R naught or elements of R, depending on what we're wanting to, how we're wanting to view the situation. And similarly, the elements M1 to M nu, etc. can be viewed as elements of M naught or elements of the aggregate M. Okay, so we start off with R1, and we, in our correspondence, we just map that to M1 up here. And then we move on to R2. So in R, R2 has a particular ordinal position relative to R1. So we're talking about in R here. So what we do is we go along from M1, and we find the least index, I2, such that Mi2 has the same ordinal position in M relative to M1 as R2 has to R1 in R. Then we move on to R3. R3 has a particular ordinal position in R relative to R1 and R2. So we go back to M0 and we start at M1 and we go along, and we find the least index I3 such that mi3 has the same ordinal position relative to m1 and mi2 in M as R3 has to R1 and R2 in R. And we continue this process. So R new has a particular ordinal position relative to R1 to R new minus 1 in R. We find the least index in M0, which is I new, such that M I new has the same ordinal position to M1, Mi2, Mi new minus 1 in M as R new has to R1 to R new minus 1 in R. And we can continue that process so that all of the R's are accounted for. So if we go through the whole of R0, then we will account for every element of R. Remember, the elements of R0 are exactly the elements of R. It's just that they're arranged in a much more convenient way for us to go through all of them. So in this way we can see that every element of R corresponds to some element of M. So what we need to show now is that every element of M is actually accounted for in here. Because the subscripts here don't necessarily it doesn't automatically mean that it accounts for M1, M2, etc. We've just got M1, Mi2, Mi3. We need to show that every element of M is actually accounted for in there. So we're going to use a kind of induction argument here. So we're going to see this as taking kind of the first however many numbers from this sequence of M1, Mi2, Mi3, etc. We take the first however many numbers from this list. Well, obviously, if we just take one number from this list, the first number, M1 is there. If we take the first two numbers, M1 is still there. Take the first three numbers, M1 is going to be there. So it doesn't matter how many numbers we take, M1 is always going to be there, and that's like the base case, really. M1 is always amongst this list of numbers that we choose. So now our inductive assumption is going to be that we can choose lambda to be large enough so that amongst the numbers M1, Mi2 to Mi lambda, we've got contains the numbers M1, M2 to M new. Okay, so that's our inductive assumption. And then we need to have a look at M new plus 1. Now it might be the case that M new plus 1 is also contained amongst these numbers here. If that's the case, then the inductive step is basically done. There's nothing else for us to do. But we need to consider the case when M new plus 1 is not amongst these numbers. Okay, so it's not amongst M1, Mi2 to Mi lambda. Now it turns out that M new plus 1 will have a certain ordinal position relative to M1, Mi2 to Mi lambda in M. Okay, so because M1, Mi2, Mi lambda correspond to the elements in R, R1 to R lambda, then because of the nature of R, there are an infinite number of elements in R that have the same ordinal relationship to R1 relative to R1, R2, R lambda as M new plus 1 has to M1, Mi2 to Mi lambda. So if we go back to R0 and we go along this sequence and we choose the least index, R lambda plus sigma. So lambda plus sigma is the least index in R0 such that R lambda plus sigma has the same ordinal position relative to R1 to R lambda as M new plus 1 has to M1, Mi2 to Mi lambda in M. So what we need to show now is that M new plus 1 cannot be found amongst this list of elements, which is a kind of extended version of our list now. So we've got the M1, Mi2 to Mi lambda, which we originally had here, but now we've tagged on mi lambda plus 1 up to mi lambda plus sigma minus 1. We need to show that m nu plus 1 is not in this list. Because if it were, then we'd have that m nu plus 1 is equal to mi mu, where lambda is less than mu is less than lambda plus sigma. Okay, well that means that mi mu would correspond to r mu. Again, mu is less than lambda plus sigma, but then that would mean that r mu has the same ordinal relationship to r1 to r lambda as m nu plus 1 has to m1 to mi lambda. But that's a contradiction, because lambda plus sigma was chosen as the least index, the least such index. So if there is a mu that is less than lambda plus sigma, then that's going to be a contradiction. So that means then that m nu plus 1 cannot be found in this list of numbers here. So m1, mi2 up to mi lambda plus sigma minus 1, m nu plus 1 is not there. So that means then that m nu plus 1 must be equal to mi lambda plus sigma. So therefore, again, we can take a long enough list of these numbers here to guarantee that m nu plus 1 is going to be there. And continuing the kind of inductive aspect of this, we'd be able to get m nu plus 2, m nu plus 3, all of the m's. And that would account for all of these m's in m naught. But remember that m naught has all of the same elements as m. So therefore, not only do we have every element of r accounted for here, mapping over to elements of m, we've also got every element of m accounted for over here. So every element of m corresponds to some element of r. So it's going to be a one-to-one relationship between the two, which of course we need. But not only that, all of these elements here that correspond to these elements over here have exactly the same ordinal relationship. All of these elements have the same ordinal relationship in m to one another as their corresponding elements have over here to one another in R. So therefore this mapping is in fact an imaging of R onto M, and therefore we can conclude that the ordinal type of M is equal to the ordinal type of R, which is equal to eta, which is exactly what we needed to show. So this theorem kind of characterises this particular ordinal type, which is eta. So let's have a look now at some of the arithmetical operations that we can do involving eta on this ordinal type eta. Then eta plus eta is equal to eta. So we can visualise eta plus eta as kind of the aggregate of rational numbers greater than 0 and less than 1, and greater than 1 and less than 2. Just a single aggregate. That is the same ordinal type as the aggregate of rational numbers greater than 0 and less than 1. Similarly, all of the rational numbers between but not including 0 and 1, between but not including 1 and 2, 2 and 3, up to eta minus 1 and eta, all gathered together into a single aggregate, will also have the same ordinal type as eta. Eta times eta, which can visualize maybe as the all of the points in the unit square on the interior of a unit square with rational coordinates, for example, has the same ordinal type as eta, and indeed any such eta dimensional generalization of this has the same ordinal type as eta. This would be, I guess, interpreted 1 plus eta times eta I guess you could visualize that as kind of the unit square, all of the interior points with rational coordinates, and maybe one of the sides. Yeah, one of the boundaries on one side. That's the same ordinal type, and you can get similar visualizations for all of these. These ones, on the other hand, are all different from eta. They have to be different from eta because this one would have a least element, which eta, the ordinal type eta, whatever aggregate we're talking about, doesn't have a least element as stipulated in the theorem that I've just proved. Similarly, this would have a greatest element, and similar interpretation, so this would have a least element and a greatest element. Nu times eta, I'm trying to think how to, I can't think how to interpret that right now. Eta plus 1 plus eta, so that's kind of all of the rational numbers from 0 to 2, between 0 and 2, not including 0 and 2, so that's maybe the visualization from that, for that one, including 1 itself has the same ordinal type as eta. However, this one, which is kind of all of the rational numbers between 0 and 1, greater than 0, less than 1, and then a few discrete points in between, and then another copy of that aggregate of rational numbers. This does not have the same ordinal type as eta, because it would be possible to find two elements of this between which there would be no other elements, which is it's not characterised. It's not a characteristic feature of eta. Also worth pointing out that eta, the inverse ordinal type, eta star, is equal to eta itself. So these are just a few of the operations and some of the relationships between eta and some of those operations. Okay, so given any simply ordered aggregate, I think it's fairly intuitive, fairly obvious that if we take any part of a simply ordered aggregate, that part itself will be a simply ordered aggregate, but not necessarily of the same ordinal type. So, in particular, parts of an aggregate M, which have the ordinal type omega or omega star, are called fundamental series of the first order in M. So M itself doesn't have to have either this ordinal type or this ordinal type. It could be very different to either of these ordinal types, but if we can extract a part that has either this ordinal type or this ordinal type, then we've got what's called a fundamental series of the first order in M. Usually we'll just call it a fundamental series. In particular, we'll refer to omega as an ascending fundamental series and omega star as a descending fundamental series. And then we've got a couple of definitions here for what it means for two fundamental series to be coherent. So here we've got what it means for two ascending or respectively descending fundamental series to be coherent. Obviously the fundamental series both have to be in M, because if we look further on, we're talking about kind of ordering between elements of one fundamental series and of the other fundamental series. This can only happen if they're in the same aggregate, really. So the fundamental series have to be obviously in the same aggregate. But I'll just talk about the case for ascending fundamental series. Two ascending fundamental series, a nu and a primed nu in M are coherent if for every element a nu there are elements a lambda primed such that a nu precedes a lambda primed, and for every element a nu primed there are a mu such that a nu primed precedes a mu, and we write in symbols this here. We can also have an ascending fundamental series and a descending fundamental series being coherent also. And what that means is that if for all nu and mu, A nu precedes B mu, and B if in M there exists at most one M naught, so there might be 1, there might be 0, such M naught, such that for all nu, A nu precedes M naught, which precedes B nu. So they're the definitions of coherent fundamental series and coherent fundamental series. I just want to have a little talk about some of the theorems that follow from this, and there is a bit more terminology that I need to introduce. I'm just going to go through the theorems quickly. I'm not going to prove them, but that's what I'm going to move on to now. So there's just a couple of theorems that I want to touch on with this fundamental series. So theorem A is if two fundamental series are coherent to a third, they're also coherent to one another. And theorem B, two fundamental series proceeding in the same direction, of which one is part of the other, are coherent. So they're kind of obvious theorems, and I'm not going to prove them. Even Cantor doesn't prove them in the book. And then we come on to the definition of this limiting element. So if we can find in our aggregate M an element M naught, such that for some ascending fundamental series in M, for every nu, such that for every nu we have a nu precedes M naught, and for every M in our aggregate M, such that M precedes M naught, there is an index nu naught, such that a nu follows M for nu greater than or equal to nu naught. And there's a similar definition for the descending fundamental series in M with just a couple of sign changes. Then such an M naught is called a limiting element of our fundamental series in M. Or we can say that M naught is a principal element of our aggregate M. So if we talk about a limiting element, we're really talking about in relation this number M naught, this element M naught in relation to the fundamental series. If we talk about M naught as being a principal element, we're talking really in relation to the aggregate from which it's come. There's no guarantee that there will be such an M naught, so just because we've got a fundamental series, ascending or descending, doesn't mean that it will have a limiting element. However, if an ascending or descending fundamental series in M does have a limiting element, that limiting element is going to be unique. And you can maybe compare this with, to a certain extent, sequences of real numbers. So if a sequence of real numbers converges, it converges to a unique limit. Now these are potentially very different objects here to real numbers. So it's not to be taken literally, but there's some analogies there regarding this limiting element kind of concept. And there's a lot of similarities here in the notation as well. So, for example, with a sequence of real numbers, for any given positive magnitude, we can always find an index n or n naught or whatever, such that the terms are closer together than this originally given magnitude. It's not exactly the same, like I say. But there's some analogies that you can draw there, and there's some more theorems then, which I'm not going to go through. There's actually a bit more terminology that I just want to quickly introduce, namely that if in M every element of our aggregate M is a principal element, then that aggregate is described as being dense in itself. Okay, so this is different. Dense in itself is different from everywhere dense. So the definition of everywhere dense was between any two elements in our aggregate, there's always a third element. But everywhere dense means that every element of our aggregate is a principal element. So in other words, it's a limiting element of some ascending fundamental some ascending or descending fundamental series. If every ascending or descending fundamental series in an aggregate has a limiting element in M, then that aggregate is called closed. Okay, so like I said, not in a general generic aggregate. If we choose obviously simply ordered, we could choose an ascending fundamental series. It might not have a limiting element in M, but if every such fundamental series that we can extract from that aggregate has a limiting element in M, then we've got a closed aggregate. And an aggregate that's both dense in itself and closed is called a perfect aggregate. And also the ordinal types that correspond to closed aggregates or everywhere dense aggregates are called everywhere dense ordinal types or everywhere dense types, and closed types or closed ordinal types, depending on the type of aggregate that we've got, or we might even have perfect types corresponding to perfect aggregates. Let's just have a quick look at some aggregates, some ordinal types of similar to the ones that we've just been discussing, so things like closed aggregates and closed ordinal types and things like that. So if we look at the ordinal type omega, which arises from an aggregate of this kind of form, then this has no principal elements. This aggregate has no principal elements. There are ascending fundamental series in there. There's many of them, but none of them have a limiting element in the aggregate. So there are no principal elements, and it's not closed either. Omega star, which is the inverse aggregate of this one, effectively. Then similarly, we can find descending fundamental series, but none of them have a limiting element in the aggregate. So there's no principal elements in this aggregate. Omega plus mu, which arises from an aggregate of this kind of form, with the obvious implied ordering there. Then this aggregate has a single principal element, which is F1, and every fundamental series is going to be an ascending fundamental series that has F1 as a limiting element. So it's closed. There's no other elements that are principal elements, just the F1. So because every fundamental series in here has F1 as its limiting element and F1 is in the aggregate, then it's a closed aggregate. But it's definitely not, for example, dense in itself, because not every element is a principal element. Omega dot 2, omega times 2. Notice it's not 2 times omega, it's definitely omega times 2. So here effectively we've got two copies of omega, one straight after the other. Again, we've got a single principal element, which is F1 here. But in this case, there are fundamental ascending series that don't have limiting elements in the aggregate. Namely, if we take F1, F2, etc., it's an ascending fundamental series in this aggregate, but there's no limiting element there. However, E1, E2, etc., all have these ascending fundamental series all have the limiting element F1. So this has some principal elements. It has F1 as a principal element, but not every fundamental series has its limiting element in the aggregate, so therefore it's not a closed aggregate. And again, it's not dense in itself. Eta, which is the ordinal type of the aggregate of rational numbers from greater than 0, less than 1. We've already seen that this is everywhere dense, so we saw this earlier in the characterisation of this ordinal type in that theorem that I proved. But it turns out that every element of R is a principal element, and therefore this is dense in itself. So not only is it everywhere dense, but it's also dense in itself. Remember, these are two different concepts. Easy to confuse, but they are definitely different concepts. But it's not closed, so it's not a perfect aggregate. And it's not closed because we could easily imagine taking maybe in the usual sense, a sequence of rational numbers which converges to 1, for instance. A monotonic increasing sequence of rational numbers converging to 1. This would be effectively an ascending fundamental series in this aggregate, but obviously 1 is not in the aggregate, so it's not closed. And then we move on to this theorem, which is the very last part of this first article of Cantor's. And this characterises the ordinal type of the linear continuum. So the linear continuum is the aggregate of real numbers between and including 0 and 1 with their usual order of precedence. So the ordinal type of this aggregate is denoted theta, and if we've got an ordered aggregate M, which is such that it is perfect, so in other words it's closed and it's dense in itself, in it is contained an aggregate S with the cardinal number of S equal to F0, such that between any two elements of M there are elements of S, then the ordinal type of M is equal to that of the linear continuum, theta. So this is quite a significant theorem. I think this would have been a very big thing for Cantor, because Cantor viewed the linear continuum as kind of a prototype standard continuum. There's something special about the linear continuum of real numbers to Cantor. So this would have been quite an important theorem. I'm not going to go through the proof of this. It's not a particularly lengthy proof, not particularly difficult. It's just I think I've gone through enough stuff already in this video. So I'm going to leave it there. I'm just going to leave the statement of the theorem there. That's everything that I'm going to cover in this video. In the next video, I'm going to move on to well orderings and transfinite ordinal numbers. But I want to thank you for watching this video, and I look forward to seeing you in the next video.